So good afternoon, everybody. I'm Pietro Inglese, and I will be explaining you a comparison about the main logic in memory implementations. My T supervisors are Giorgio Natale and Joanna Ratagelu. First of all, I will start with a brief introduction on the computation in memory and the computation, the possibility of computations that are available. Then I will go through the state of the art, the exploration on the logic in memory that I did, and finally the electric simulations that I performed. So in order to give the first idea of what is the computation in memory, I will start showing a classification of the computing possibilities. The first one, that is the one that we are the most used to, is the typical one, having the CPU and the memory separated, connected through a bus, where the CPU will have to perform a computation. So we'll read the data from the memory, we'll perform the computation, and we'll then write the result back to the memory. Since this can be slow, there can be a way to make it faster. For example, what you can see here is called the near memory computing, that consists basically in putting the memory as close as possible to the CPU, reducing therefore the latency caused by the bus. Another way could be directly pre-compute the results with the CPU, save them in a lookup table in the memory, and then retrieving them just with the use of a key, therefore making the computation itself not necessary exactly on the moment, since the results will be pre-computed. This is called computation via lookup table. And finally, there is the computation in memory that is done by using the memory itself to perform computations. And therefore, the computation will be done inside the memory or in its periphery. As you can see here, the two colors were showing the ALU and the memory. And the last case has the ALU and the memory all together in the same place. What I will focus my attention to is the computation in memory. So the last one. Regarding the state of the art, in order to classify the computation in memory, we can say that there are, first of all, two types of computation that can be performed. Both of them exploiting the physical memory device characteristics, and are the analog and the digital. The analog computations are used to perform additions and matrix multiplications. So these are typically used for the design of accelerators and typically are used for machine learning implementations. The digital computations are, on the other hand, used to accelerate the so-called Boolean logic. And in this case, the arithmetic logic unit, the ALU, is embedded in the processor and is used directly inside the memory. So the memory itself is acting as ALU. Another classification to a sub-level, so what I'm focusing on mostly is the logic in memory, that is a subset that is basically the digital kind of computation. So I will leave the analog computing on the side. I will not talk about it. On another subset of the computation, of the classification, we can see where the inputs are stored to perform the computing. And these two, the possibility are inside the memory itself. So the inputs are stored as memory content. And in this case, we are talking about stateful logic, or they are stored as an electrical signal. then we're talking about a non-stateful logic. The final type of classification is regarding where the computation is executed. Is it executed only in the memory array, in the memory array and in its additional circuitry, or in both? Therefore, the in-memory computing solutions are, the first one is the stateful logic in memory array. So we're talking about a logic where the inputs are stored in the memory and the execution of the logic in memory is done inside the logic in memory array. Among these, I want to show you the magic, the imply, and the stateful two-input logic. Then we have the stateful logic in the logic in memory array and its periphery. So we are talking about the computation whose inputs are stored in the memory, but the computation itself is performed inside the array and exploiting its periphery. And finally, in the non-stateful logic, in the logic in memory array and its periphery. In this case, the inputs are hybrid and they are both as memory and as electrical signals. In this case, I will talk about the PLIM solution. So the first one, the stateful logic in memory array, it is done by the magic that, as you can see here, the schematic is made of 2 memristors where the inputs are stored, and then another memristor in series that is where the output is stored. The magic implementation uses as main solution, as main operation, the NOR operation. Then we have the imply solution that, as you can see, there are 2 memristors and one of those is both input and output. And then finally, we have the stateful two-input logic that can be seen as an extension of the imply, where there are 3 memristors and one of them is the output as well. While the imply performs the implication logic, the stateful two-input logic performs the so-called OR-NOR, meaning that it performs the NOR between 2 inputs, and finally it ORs it with the third input. Finally, the stateful logic in memory array and its periphery, it's the one that is done in the logic memory array and in the periphery. So we are talking about a solution that exploits the sense amplifier, and in some cases, in order to do other operations, we use an additional logic in addition to the sense amplifier. As you can see here, there are 2 inputs, but there can also be 3 inputs. And the operations that are possible are NAND, AND, NOR, OR, and then, and AND. And this can be done both with 2 and 3 inputs. And then adding additional logic, we can have the XOR and the XNOR for 2 inputs and the full adder for 2 inputs. Also for 3 inputs, we have the minority and the majority operators. This is a solution that is done only by modifying the sense amplifier. So it can be used with more memory technologies than the previous one that can only be used with memristors. The third solution is the PLIM, the programmable logic in memory. And this exploits 1 memristors on which 2 different voltages that are represented by the 2 inputs that we want that are applied on the memristor to perform the operation. The output, as I said before, the output is stored in the memristor that will also have the value of one of the three inputs. The operation that is performed is the resistive majority. That is basically the majority operator done onto the first input, the second input negated, and the third input. Having in mind that these three different solutions, three different classes with the 5 solutions that I presented you, what I've done is a manual mapping of the various solutions. And now I will show you an example. For example, taking the magic, the imply, the resistive majority, and the or-nor tree, that in this case is the same as the imply, and trying to perform a logic and following the steps that should be done with the solutions I put here, you can see that there are different steps, and there are used a different number of memristors, meaning that these solutions have quite important differences among them in terms of steps that have to be used and also inputs and voltages that have to be provided. Therefore, we performed a comparison on the operations that we had. First of all, the idea was to do an electrical characterization on the area, the performance, and the power consumption. To do that, we started with a manual mapping, that is the one that I showed you before with the example, to have the area related to the memory of the elements and the performance related to the logic steps necessary to perform an operation. And then we passed it to the simulation in order to have the performance in order with the total time. And with the simulation, we will be able also to then having the needed data to also calculate the power consumption. We did this comparison on several logic functions that are true, false, not and copy, and NAND, or, NOR, XOR, XNOR, imply, and negated imply, and finally with the full adder, in order to compare all of them. Here you can see a result that we had. Is not the most extended one because otherwise I cannot show it. But for example, let's go seeing what happens in the NOR operation. In the NOR operation, that is the basic operation for the magic, we can see that we need 3 memristors and 2 steps. With the imply, that is faster doing other operation, you can see that we need 9 steps, that is quite high. And finally, with the or-nor, we only need 2 steps. So like the magic. The majority in this case needs 6 steps. The final benchmark can be done with the full adder. And as you can see here, the full adder needs a whole different number of steps and of elements, more of steps than on elements, regarding for the operation that is executed and the solution that has been chosen. In this case, you can see that there is a lot of complexity. And this shows that depending on the implementation chosen, there can be the necessity of really, not the necessity, sorry, there can be a very big difference in terms of performance. So after this, we identified the problems, such as at the circuit level, the availability and the accuracy of the electrical models, because, for example, for the availability, now we are using the VT model, that is the one that the researchers of magic are using. But it's not easy to find, so to get the whole simulation environment. And it's also important to test with other models that we are currently preparing our whole simulation environment to do. On the other hand, we noticed that there are quite big electrical constraints in terms of timing, resistive value, and input voltages. And this could be also connected with the reliability issues, because if we have strong constraints, then the reliability could be really important in terms of the correct functioning of the operations. And finally, at system level, we noticed that not all the solutions have a control unit and instruction set architecture or a microarchitecture. To go and really understand the electrical constraints and the reliability issues, we decided to perform electric simulations. For now, we are deeply analyzing the MAGIC solution with its extensions to understand which are the constraints and electrical problems that we can face. And we are preparing the other solutions, such as Imply and Honor Tree, for performing the same analysis on them. I wanted to show you, for example, the result of the MAGIC NOR. As you can see here, the idea is that we ran a simulation with the MAGIC NOR operation, with the different durations of the NOR operation and different input voltages. The area where the NOR operation is correctly executed is the dark green, so this one. The light green area is an area where the output is correct, but one of the inputs is not correct anymore, meaning that there has been the so-called input destruction. That is what we try to avoid, since if we want to do a more complex operation and we want to reuse the inputs, we need them not to change. So as you can see here, there is quite some space in terms of time and of voltages to then have the correct results, also in terms of feasibility from the physical point of view. But this is the Felix-OR, that is an extension of the MAGIC. And as you can see here, the area is way smaller, meaning that there is a necessity of strong constraints on the input duration and the voltages, and therefore there will be the necessity of a higher precision to then have the right result of the calculation and of the operation. Thank you for your attention. Here I leave you some bibliography, and if there are questions, I'm here. Thank you.